Today is the second and last lesson of Unit 5, and we know from this entire course that linear relations, when graphed, creates a straight line, and we represent it with the equation y is equal to mx plus b. Non-linear relations, when graphed, would not be a straight line. So in grade 10 math, you'll learn more about nonlinear relations. So grade 9 is like 95% linear relations, and then grade 10 is all about nonlinear relations. So today we're just going to distinguish between what the difference would be when you graph a linear relation compared to a nonlinear relation. And all really it is it a straight line? If so, it's a linear relation. If it's not a straight line, then it's a nonlinear relation. A line of best fit is a straight line that comes closest to the points on a scatter plot of a nonlinear relation. Okay, so if it can go through all the points, then that's great. If it can't go through all the points, then you're going to try to go through as many points as possible, but keeping in mind that you should have the same number of points on both sides of the line. And there's an example here for you. So when the graph data falls into a nonlinear pattern, a curve of best fit is used to show the relationship between the set of data points. A COBF, curve of best fit, is used on a scatter plot of a nonlinear relation. So in this example, the points on the scatter plot do not reflect a straight line. So drawing a line of best fit would not appropriately represent the data points. Okay, so if I drew a line of best fit, it would not appropriately represent the direction of my points. My points are moving in a curve-like direction. So we would draw a curve of best fit, but following the same guidelines as creating a line of best fit. You want to go through as many points as possible when drawing your curve of best fit. If you can't go through all the points, then try to balance the same number of points on the left and the right side of the curve of best fit. So in these examples below, you can pretty much draw your curve of best fit through all of the points. So let's do that now. Okay, so if I'm able to go through all the points, then I will, and I can. Okay, and the next one, I could pretty much go through all the points and see the same thing. Okay, I think that I didn't go through one or two at the top here, but pretty much we went through all of them. So now it's asking us to describe the trends in the data. So remember, trends means the pattern of our points. So I would say that from time 0 seconds to 1 second, our points are moving in an upward direction. The height is increasing. Then after 1 second, our points are moving in a downward direction, which means that our height is decreasing. So I'm going to say the height increases to 1 second, then decreases after 1 second. Next, so this is comparing the year and number of animals. So our information starts at 1980. So the number of animals from 1980, well, all of like the entire set of data points shows that our points are, or the number of animals are increasing. But it's creating this curve, which means that from 1980 to about 1988, this curve is increasing, but then after 1988, it sort of increases at a more rapid pace. Okay, so that's why this on the second half of our curve, our curve is getting steeper. It's more steeper because the number of animals are increasing at a faster rate. Okay, so if this was a straight line, let's say that our points were creating a linear relation. So we would draw a line of best fit. That means that our number of animals would increase at a constant number the entire time, right? So they would have the same slope from 1980 to 1996. However, this curve tells us that the slope is continuing to change from year to year. So from 1980 to 1988, it is increasing, but it's increasing at a faster rate beyond 1988. And that's why you get this sort of steeper slope than prior to 1988. Okay, and in C, so the height is increasing, all right, to day 20, I would say it's increasing, okay? And then it's increasing after day 20, it's increasing at a more rapid pace to about day 50. Okay, so do you see how the slope is more steeper now? And then after day 50, it sort of slows down again. Okay, so height increases to day 20, then rapidly increases from day 20 to 50, then stabilizes after day 50. All right. Creating an equation of a line of best fit. So going back to line of best fit, we can actually create an equation of our line of best fit. Now we would follow the same steps as to creating an equation of any straight line. Okay, so we would pick 2 points on the line, use a slope formula to find the slope. Then we would find B by substituting 1 point on the line and their slope, and then we would create an equation. Now, when creating a line of best fit, we just need to make sure that our points are on the line of best fit and not points that are not on the line of best fit. Okay, so we're going to practice creating an equation of the line of best fit here. But first, it's asking us to plot all our points on this graph, and then we'll draw a line of best fit and then create an equation of the line of best fit. Let's just answer A. It's asking us to identify the independent variable and the dependent variable. Okay, so this shows the number of days absent from mathematics class and the math marks for 15 students. So again, we understand that a horizontal table of values, the top row would be our independent value, but also just thinking about it, which one depends on the other? Does the number of days absent depend on your math mark, or does your math mark depend on how many days you were absent? So it's most likely, we haven't plotted the points yet, but it's most likely that the more days you're absent from class, the lower your mark will be because you've missed so many lessons, right? So every day, every class that you miss, you're falling farther and further behind. Okay, so creating my scatter plot, I'm going to include a title. I'm going to number and label my axes. And then I'm just going to plot my points. Okay, so I have plotted all of my points. Now I'm going to draw a line of best fit, making sure that I either go through as many points as possible, but making sure that I have the same number of points on the left and right side of my line. Okay, so I have drawn my line of best fit. Yours may be slightly different than mine, and that's okay. Now I'm going to create an equation of the line. So my equation is going to be in y is equal to mx plus b form. I'm going to start off by picking 2 points on the line, okay? So any point, any blue point that is not on the line of best fit cannot be used. This is an equation of the red line, which is our line of best fit. So we need to pick points that are on that line, okay? So I pretty much only went through 1 or 2 blue points. So I can use those points, or if you didn't go through any of the points, you can just pick points that follow the grid lines that are easy to read. Like this one, that's 844. And this one, which is 14, oops, no. This is 860, sorry, and this one's 1444. So I'm going to use those 2 points that I've identified. And my equation is going to be in y is equal to mx plus b form. So I'm going to let y represent the student's math mark. And I'm going to let x represent the number of days absent. So I'm going to start off by finding my slope using the 2 points that I found. So since reading from left to right, this point comes first. This is going to be my x1, y1. This will be my x2, y2. Okay, so you're going to, depending on what points you picked, because like I said, we're not going to have the exact same line of best fit, which means we're not going to have the exact same points, which means we're not going to have the exact same slope. But it should be fairly close to mine. And I'm going to actually convert my slope into decimal form, because when we're graphing, it's very difficult for us to graph -8/3. But it is easier for us to know where -2.67 is. And now I'm going to use one of my points. I'm going to use 860 and my slope to find b. And again, I'm going to convert my b into decimal form just because it's easier to graph with decimals than fractions. then putting it all together, we created an equation of our line of best fit. Okay, so again, your equation may be slightly different than mine, but what I like to do is I just like to double check to make sure that my line of best fit equation is pretty accurate by locating the b value on the graph. So 81 is pretty much right here, and that is where my y-intercept is. So I do think that it is appropriate. And I did get a negative slope, which does, like, this is a negative relation. So I think that my equation for my line of best fit is pretty accurate. Okay, describe the relationship between the student's marks and attendance. Okay, so we can read the graph and we can determine that as the number of days absent increases, the student's mark decreases. And that's how we get that negative slope. Okay, so as our x variable increases, our y variable decreases. That is a negative relationship. So using the line of best fit equation that we created, estimate the number of students absent for 8 days. Okay, so 8 days is here. So remember, we can use interpolation, which is just reading the graph. Okay. Or we can use our line of our equation that we've created, which is still interpolation, but just estimating algebraically. Okay, so 8 days. That means that I'm going to sub x for 8 for x, and I'm going to solve for y. Okay, so this is about 60%. So when a student is absent 8 days, we're estimating that they will receive about 60%. And by just reading the dotted purple lines, that is what we would get if we interpolated just reading the graph as well. Using the line of best fit equation to estimate the mark for a student absent for 26 days. Okay, so now our x, we're going to sub in 26 for x. Okay, so 26 days would be here. So that would be extrapolation because we would have to extend our line of best fit. If we were estimating just reading the graph, we would have to extend our line of best fit and then read. Okay, so extrapolating, but algebraically. So this is about 12%. So when a student is absent for 26 days, they will receive about a mark of 12%. A distance time graph is a graph that shows how distance varies over time. So here is an example of a distance time graph. So it's always time and distance. Our time is always our x or independent variable, and our distance is always our y. Okay, so what is your distance over a certain time? Measuring speed. Speed is how fast something is moving. Often occurs while analyzing intervals in a distance time graph. So we usually measure speed when we're dealing with distance time graphs. Now it says the word intervals. So the intervals represent the different directions that occur throughout the graph. So this is one interval from here to here. Okay, this is interval 1, let's say. And then from here to here is interval 2, and then from here to here is interval 3. Because the direction or the movement of whoever we're analyzing this graph is changing 3 times in this graph. So we just divide them into intervals. So we can measure speed of all 3 intervals. Okay, so we can measure the speed of this interval, and then this interval. They would have different speeds. To calculate the speed, you would divide distance by the time. So speed is equal to distance over time. Okay, so y over x. So where have we seen that before? Well, change in y over change in x is actually how we calculate slope. So to calculate speed is the same way that we would calculate slope. So the steeper the line or the slope, the faster someone is moving. Okay, so the steeper the line, the faster they're moving. Remember, we were talking about that back here when we were analyzing these curve of best fits. The steeper the line, the faster something was moving or accumulating. Okay, so it's the same thing. So the steeper a slope, the faster someone is moving when we're dealing with a distance time graph. Okay, so speed and slope are calculated the same way. However, we've learned from back in the beginning of this course that slope doesn't ever have any units, but speed does. So speed here would be hours and kilometers per hour. Okay, so the difference between speed and slope is that speed is a unit rate. Okay, and whereas slope is a ratio, and that's why speed gets units and slope doesn't. Okay, so another way of finding speed, finding slope, is called finding the rate of change. Okay, so rate of change is basically means you're finding the unit rate but adding units. Okay, so you're dividing distance over time and then you're just including units at the end, kilometers per hour. Okay, so unit rate, a rate of change, unit rate, it's all the same thing. You need to make sure that you have 2 units. Okay, so when you're finding speed, your units at the end isn't going to be kilometers and it's not going to be hours, it's going to be both kilometers per hour. So how fast someone is running, you don't say they're running, let's say 10 kilometers, or they're not running 10 hours, they're running 10 kilometers per hour. So that's called a unit rate when you have 2 units together. And the units we always get from our x and y value. Our x and y values would determine what the units would be at the end. Okay. All right, so these are just, there's a lot of new terms here, but they all mean the same thing. To find slope, we know it's rise over run, change in y over change in x. Okay. To find a unit rate, we would use rate of change, which is slope. It's all the same. So speed is an example of a unit rate. So we would find the rate of change. How is the distance in time changing over one of the intervals? Okay, so it's really just y over x. You take your y value and divide it by your x value. Okay, and you just include 2 units at the end. So let's practice reading distance time graphs and calculating speed in these examples below. My graph 1 didn't appear for some reason, so I just drew what you have on your paper for graph 1 here on graph 2. Okay. So it's asking us to identify the initial location of the runner. So this is a graph of someone running. Okay, so they're running a certain distance over time. So it says here distance from the starting line. Okay, so if you're 0 meters away from a starting line, that means that you're on the starting line. So at 0, 0, this runner is on the starting line. That is the runner's initial location. So that's 0.00. Describe the runner's motion and then calculate the speed. So this person, this runner, because this is a straight line, it tells us that this runner is running at a constant speed the entire 4 seconds, right? 0 to 4 seconds. The runner is running at a constant speed, which creates that straight line. So to calculate speed, speed is equal to distance over time, or change in y over change in x. So my change in y, so from 0 to 40 meters, so my y value is changing 40 meters. And my x from 0 to 4 seconds, so that's changing in 4 seconds. There's a change of 4 seconds. So 40 over, so that's 40 meters in 4 seconds. So 40 divided by 4 is 10. Now remember, this is a unit rate, so we need to include both units. So my units are going to be my numerator per my denominator. Meters per second. What is the position of the runner at 1 second? At 1 second, the runner is 10 meters away from the starting line. So that's 0.110. When is the runner on the 30-meter line? So when means it's asking for the time. So 30 meters away from the starting line is 3 seconds after the runner started running. So that is 0.330. Okay, example 2. So I'm just going to erase this because this was my graph 1. Okay, create a graph of a runner who starts at the 20-meter line. So starting at 0 seconds, at the 20-meter line. Okay, and then runs to the 40-meter line in 2 seconds. So after 2 seconds from the runner starting, the runner is at the 40-meter line and then finishes at the 30-meter line. Okay, and now let's just connect our points. What is the y-intercept of your graph? B is equal to 20. What does the y-intercept tell you about the runner? Well, it tells me that the runner didn't start at the starting line, okay, because our y-axis is still the distance from the starting line. So this runner, didn't actually start at the starting line. This runner started 20 meters away from the starting line. So in graph 3, what is the initial location of the runner? 20 meters away from the starting line. Describe the runner's motion and calculate the speed. Well, at 0 seconds, the runner is 20 meters away from the starting line. At 1 second, the runner is 20 meters away from the starting line. At 2 seconds, the runner is still 20 meters away from the starting line. This runner hasn't moved. 1, 2, 3, 4 seconds has passed. This runner is still 20 meters away from the starting line. This creates a horizontal line. So it's asking us to calculate the speed. Now remember, calculating speed is the same way we calculate slope. So I'm going to expect that I'm going to get a speed of 0 meters per second, which makes sense. When you're standing in one place, your speed is 0. And so this horizontal line, also we know that the slope would be 0. So describe the runner's motion. No movement. Speed equals distance over time or change in y over change in x. Okay, so the distance, well, from 0 to 4 seconds, there's no movement, right? So the distance hasn't changed. It's still 20 meters. So they haven't moved from that place. So they haven't made any distance. So the distance here is 0. 0 meters. They've moved 0 meters in 4 seconds. 0 divided by anything is 0. And then I'm going to take my numerator units per my denominator units. And that's it. Example 4. Create a graph of a runner that starts at the starting line, runs 14 meters in 1 second. So in 1 second, they've run 14 meters, rests for 2 seconds. Okay, so 2 seconds after 1 second is 3 seconds. And they're at the same, right, because they're resting. So they're at the same location after 2 seconds. And then runs back to the starting line in 1 second. So now they're at 3 seconds. 1 second after 3 seconds is 4 seconds, and they go back to the starting line. Okay, and let's connect our points. In general, how does a distance time graph show you which direction the runner is moving? So the direction now. Well, if 0, 0, 0 is the starting line, okay, right here at this point, it tells us that the runner is 12 meters away from the starting line. So when our line is moving upwards, is rising, that means that our runner is moving away from the starting line. Okay, away. Okay, then we know horizontal lines mean resting. And then that here, in the last second, the runner is moving towards the starting line. Okay, so a rising line means that the runner is running away from starting line. And a falling line means running towards the starting line. And when the runner is at rest, that's represented by a horizontal line. Okay, so distance time graphs are just a different way of reading a graph. Okay, so the last example here, graph 5, where does the runner start? Well, 0, 0, that's the starting line. Where will the runner be at t is equal to 2 seconds? Where will he be? 10 meters from the starting line. Okay, where will he be at 4 seconds? So 4 seconds, 40 meters from the starting line. Calculate the speed of both time intervals. Okay, so remember, this is one interval, and this is another interval. Okay. And when is the runner moving most quickly? Well, we can already just see from looking at the steepness of the line that it's probably going to be interval 2. Okay, because it's a steeper line, but we're going to just algebraically calculate the speed. Okay, so interval 1, and then we'll do interval 2 over here. So speed equals distance over time. So the distance of interval 1 is 10 meters over 2 seconds. 10 meters in 2 seconds. So that's 5 meters per second. Interval 2. Okay, so interval 2 is starting at 10 meters and ends at 40 meters. So the distance there is 30 meters. And the time starts at 2 seconds and ends at 4 seconds. So that's 2 seconds. So again, we confirm that 15 meters per second is faster than 5 meters per second.